Okay, so first of all, let me apologize for the nearly a month of delay between the meshing and the Fluent tutorials, but I have been busy with some CFD of a wind turbine, and about a week ago my power supply died, so my PC was out of commission. So let's continue. You would right click on the setup and edit. Okay. Several things available in the launcher window for Fluent. The first thing to mention is 3D is already pre-selected and grayed out here because our whole case in Workbench is 3D, which is set here in the geometry, okay, analysis type. One thing to mention for anyone who is thinking of doing 2D analysis, when you start with a geometry, so let's say you would double click a new geometry. Okay. Here you want to select the 2D first before going in and creating any geometry, because once you go in, and even if you created some planar geometry, which would be two-dimensional, the Workbench would not let you switch the analysis type later. So make sure to pre-select 2D and then go about creating or importing your geometry. Okay, so that's why this is grayed out here and we cannot change it. Next thing I like to do is I remove the Workbench color scheme, because that means the Fluent window for graphics and convergence monitors for drag, lift and the moment or whatever else will be in that blue to white gradient, and sometimes the white lines or some other colored lines are not really all that visible. Okay, so untick that and all the monitors will be black background. Next thing to choose is single precision or double. Single is obviously when this is unticked, so double, single. This one you need to choose for yourself and basically test, but a single precision will go down to about 8 decimal places, and the double precision will go down to 16 decimal places. And Fluent, well, there is data available in the documentation where they recommend, if you are doing anything with geometry which is very thin in one direction and very long in the other direction, then you need double precision to kind of capture it. Or if you have very small cell sizes ranging to very large cell sizes in a single mesh, then also you need double precision, but you can kind of compare and research for yourself. Double precision obviously takes, well, nearly 2 times the memory and around 50% more solving time. So for now we will leave it in single precision, and later on I will just show you how the results differ for a double precision case. So I will do that one without recording it and then just share the results in a video afterwards. So single precision for now, so we get through it faster. And since I have a multi-core CPU, I will be switching to parallel here and using 7 threads, which would amount to 7 cores, so 1 remains for the recording, and so that everything works smoothly. And click OK. Fluent is launched, and you can see on the top here it says it's a 3D case. It's a pressure-based solver for Navier-Stokes, and it's a laminar model by default. Now it spawned all the nodes here, which are the Fluent threads, and now it's partitioning the mesh, and that's it. Okay, so here's our mesh which we finished last time. The faces, so the blue face at the front is the velocity inlet, the red face presents a pressure outlet, and all the yellow ones are the symmetries. Okay, and the bottom is white, which is a regular wall, same as the car. So this is our symmetry plane, and we specified a symmetry for the top and the left side of the domain, which basically means it's a no shear wall. So there are no shear or viscous forces acting there. That's why I just assigned it a symmetry in the meshing application. So the body is a wall and the road is the wall also. Okay, first thing you would probably do is go under mesh and check, or just click check here. And what you want to check for is are the dimensions of your domain correct? Because basically, well, it will not happen in Workbench because Workbench keeps track of units, but if you made your mesh in ANSYS CFD or ANSYS or any other meshing application which can do kind of dimensionless units, then it might happen that after you import the mesh, your domain would be, let's say, 7.5 to the power of +3. And that would mean it's 7.5 kilometers long. And then you would go, all the values would be to the power of 3 or power of -3 or whatever. And then you would go scale. And you would specify a scaling factor. If the domain was to the power of 3, you would specify 0.001, which would be dividing it by 1,000. So in all three fields. If the mesh was to the power of -3, you would specify the scaling factor of 1,000. So everything needs to be in meters, for example. Or you can change the unit in Fluent, but I like to keep it in the SI system. So close that. The other thing to check for is the minimum volume. Make sure that even though this is relatively small, it can be to the power of -13 or whatever, it needs to be positive. If it's a negative volume, that presents a large problem for Fluent, and it would already be screaming and sending out messages that there's a negative volume. You can either try to repair it from Fluent with there are textual interface commands for repairing the mesh and the negative volume, or you can go back to your meshing application and fix it there. Okay, next thing is to kind of select all of these here. So you have a pressure-based and a density-based solver. We're going to be using the pressure-based solver because our flow is going to be considered incompressible, which means that the density will be constant. There are no changes. If the vehicle was traveling at high velocities, such as approaching the Mach number of 1 or even above, then there would be effects like cavitation and density changes locally around the vehicle, and then you would use a density-based solver. Even though the pressure-based solver can solve for compressible flows, but I think density-based is more accurate for that purpose. The next thing is the velocity formulation. Basically, you leave this as absolute for anything other than, let's say, rotating turbo machinery or something where you would have a rotating frame of motion for your blades and for the air around them. And although even that can be solved in an absolute velocity formulation, which just means it's kind of looking at the velocities from the outside. So you are outside of the system, and that will mean that it will take a longer time to converge, and the displaying of the velocity fields and stuff like that is more complex. So you would use a relative formulation for that. For now, absolute, and leave it like that. The other thing is steady versus transient. We're going to be using a steady simulation because generally transient is much more complex, and it should be used when you cannot solve your case with a steady simulation. How do you recognize if you need a transient simulation? You might check the Fluent Germany paper that I uploaded. Well, I've put a link in the YouTube description for the first two parts, and you can read it there. Basically, if your monitors for drag and lift are noisy, which would mean they kind of follow a sinusoidal curve, or well, a slight sinus curve can be okay, and you can still say, okay, it's an average of some number. But if it has a very large amplitude or something like that, you would switch to transient and then select your time step to capture all of the flow features, which are transient by nature. Okay, for now, steady. We are not going to use the gravity because it does not affect the results in any significant way for horizontal flows. You would use gravity if you had a multi-phase flow with, let's say, droplets of water inside, or sand, or any heavy particles, or if your flow was inherently vertical or something like that. For now, no gravity and steady. So basically everything remains as default. The way to set up Fluent is you would follow this menu on the left, this tree here, and you would go in sequence from one tab to the other. So next thing, we're going to go to Turbulence models. If you were trying to investigate the effects of, let's say, exhaust gases or very hot exhaust gases, you would need to turn on the energy equation, which just means that it would solve for temperature and heat next to all the other equations that it will be solving. But we are not going to do that, and obviously energy equation is needed to capture the viscous heating and those types of effects, which we are also going to ignore for now. Okay, next thing, you would choose your model. You can either edit or double click, and the default is the laminar model, which we are not going to be using. It's a simple one equation model, and it solves pretty quickly, but it's not really accurate for our purposes. As Fluent Germany recommends, we are going to be using a K epsilon, and we're going to be using a realizable K epsilon. You can read all about what this is and what this means and how does it compare to the standard K epsilon model in the Fluent documentation and help files. Basically realizable here, and then we're going to use the non-equilibrium wall functions because they perform better for adverse pressure gradients, and they can cope much better with flow separation and reattachment, which is which happens often in vehicle aerodynamics. The other option is the enhanced wall treatment, which would mean that you would be solving the boundary layer with the mesh itself. So enhanced wall treatments require the y plus in the magnitudes of 1. So y plus needs to be equal to 1, which would mean the first cell would be very, very low, and the whole boundary layer needs to be resolved by at least 10 or 20 layers and layers of prisms, and you would need at least 10 of those in the inner layer, which would be the viscous sublayer, the buffer layer, and the part of the log law of the inner layer. So I did all of these investigations in my beginnings of vehicle aerodynamics, and basically I tested all of these first three, and the mesh for the enhanced wall treatment was almost three times the size of these two, which share the mesh, and all of these elements were basically in the boundary layer itself. So the element count grows very rapidly, and it should be used only if you are very, very sure that that some complicated near wall effects are taking place. So other than that, non-equilibrium will be fine. Basically, I looked at a velocity cut plot in the symmetry plane, or I was using a full car model back then, so it was the center line plane of the car, and the velocity cut plane for non-equilibrium and enhanced wall treatment was the same. When you looked at the difference between the two, it was almost not visible, and the standard wall functions failed to predict the separation that will be happening over this transition from the horizontal surface to the rear slant. So non-equilibrium is the best option, and the Fluent Germany also recommends this, and now you have a small explanation of why they did that. So realizable K epsilon and non-equilibrium wall functions. Click OK. Well, you shouldn't be touching any of these constants unless you are very sure about why you're doing it, and if you're a very experienced user, which I'm not, so we'll leave them as default. They're basically put in to be very robust, and they will provide a good solution. So click OK.